Hi, my name is Fatima Debek, and my project is on microbial corrosion, where I assessed the corrosion potential of microbes in oil fields to learn how to better prevent pipeline leaks. So, why should we care? Well, the Alberta Energy Regulator reports that in Alberta, there's enough pipeline length to cross Canada 59 times. So, any leak or hole is catastrophic. And pipelines don't even have to carry oil. The June 2024 major feeder break in Calgary, for example, shows why it's important we study how pipelines fail and why. In 2016, it was reported that 2.5 trillion US dollars per year is spent on mitigating corrosion. Previous work has found 55% of pipeline failures are due to internal corrosion, and analyses showed specific microorganisms around these failure points. These are sulfate-reducing microorganisms, or SRMs, which are known to be corrosive. They have a unique metabolism in which they breathe in sulfate and produce hydrogen sulfide. SRMs don't need oxygen, and they have been found to use oil as their nutrient source, so they can live inside pipelines. As they produce hydrogen sulfide, it reacts with the pipeline iron to make corrosive iron sulfide. This makes holes in pipelines. So, what can we do? Well, we can use industrial chemical treatments to kill SRMs. My study is novel because it tests the potential effects of SMP, or sodium nitroprusside, which is a compound used in human medicine that could also be effective in this case as well, and potentially safer than the other chemicals we currently use. But wait, every single study that I've mentioned so far has only been done under more typical temperatures and low salt presence. We don't actually have much literature that looks at the effect of these chemical treatments under really high temperature, like greater than 50 degrees Celsius, or really high salt, like up to 4 times saltier than seawater. And finally, we don't even know if corrosive SRMs even exist under these conditions. This means there is a gap to fill. So this brings us to my research questions. I took samples of oil fields at really high temperature and salt, and I wanted to know if the microbes inside are corrosive in the first place, and if they can be killed by SMP to stop the iron sulfide, and if the high salt and temperature also contributes to chemical corrosion. So, firstly, I took the fluid from the oil fields, as I mentioned, and I simulated the pipeline conditions inside these little oxygen-free bottles. I added nutrients and our metal, which were these 3 carbon steel beads. Then I added my SMP, and then I measured the hydrogen sulfide production of each bottle to see if the microbes were growing or not. And then after 90 days, I stopped the experiment, and then I opened the bottles to see what the beads look like. And here's what I found. So this graph shows the hydrogen sulfide production of a 1.4 molar salinity culture, or 2 times seawater, which is growing at 55 degrees Celsius. I dosed it with different amounts of SMP. The black line on top is bottles grown without any SMP, which shows a steady hydrogen sulfide increase over time. When I dosed it with 150 ppm SMP, there was less hydrogen sulfide being produced, and in the bottles with the most SMP, there was no growth of the SRMs at all. So SMP was effectively able to inhibit SRM growth and hydrogen sulfide production. But what about corrosion? Well, here's the beads before the experiment. A here is the beads after 90 days and salt only. We can see some pits. B here is showing the lower SMP concentrations with the microbes. Still see some pits. C here shows the high SMP concentration with SRM, which also shows the most corrosion that we've seen so far. And then here we have D, which is SMP all by itself, no microbes at all. This is where I saw the most pitting, and the beads were completely destroyed. So, what happened? Basically, the SRMs were not corrosive by themselves, and I saw that the high salinity of the samples contributed more to corrosion to the beads than the SRMs. And I also saw that SMP was the greatest contributor to corrosion by itself when there were no other microorganisms. And with that same dose of SMP, if there were microbes there, then the destructive effect of SMP was decreased. So does this imply that the presence of the SRMs protected the metal from SMP? Yep. And this implication that microbes are not as bad as we thought under these more extreme conditions, which was the opposite of what we were expecting, is a novel finding of my study. Thank you.